Hello, my name is Daniel Lin Calera, and today I'll be presenting my research on using geometric morphometric analyses to differentiate the SB and SC elements of the chondron species Dapsilotus obliquicostatus. This was made possible with funding for the McNair Scholars Program at Texas Tech University, with assistance from my mentor, Dr. Neil McAdams. So before we dive into the research, let's make sure that we're all on the right track by giving some background information first on these few topics. Let's begin with the chondron. Chondrons were small eel-like animals that lived from the late Cambrian up into the early Jurassic, so they lived for about 300 million years. We can tell their range of existence by looking at their fossils, shown here. Chondrons are typically only preserved in the form of their mouth parts. These parts would form an apparatus inside the mouth of the chondron, shown here. But unfortunately, these apparatuses are not usually preserved in full, as they have a tendency to fall apart upon death. Luckily, conodont fossils can be quite numerous, so we've managed to piece together approximations of what we believe to be the apparatus of a few well-documented species. Here's a view of what we believe the typical assemblage of conodont to be in real life. Dapsilotus obliquicostatus was a conodont species that lived during the Silurian period that is represented entirely by coniform elements, shown here. The SBC elements pictured here exhibit a noticeable difference in morphology. The top row represents the regular morphotype, while the bottom row represents the curved morphotype. Our research question is whether this difference is equivalent to distinct SB and SC elements. In the case of Dapsilotus obliquicostatus, the lines separating separate elements can be blurry. We chose to study Dapsilotus obliquicostatus because the apparatus of the species contains a symmetry transition series in the S elements of the assemblage. These consist of the SA, SB, SC, and the M elements. For the purpose of this study, the SB and SC elements are of the most importance, as the gradation from SB to SC is extremely fine and makes any attempt to distinguish between them with the naked eye nearly impossible. To remedy this, we can turn to software to help us make these fine distinctions. Landmark-based geometric morphometrics is a study of shape through geometrically arranged Cartesian coordinates to observe morphological variability. What this means is that we can assign discrete points to certain features on a selection of fossils to find subtle differences in morphology between specimens. This software has been used in previous research to examine more robust elements in chondron assemblages, such as platforms and ramiforms. However, there is no precedent for morphometric work done on coniform chondron elements. So this study also served as a way to prove that coniform elements can in fact be studied in this way. These figures are wireframes generated from this study that help illustrate how the landmarks shift from specimen to specimen. You can see the curved, shown here, and the regular forms, shown here, represented by the frames. We'll look at these in more detail later on. These are the morphometric programs we used during this study to analyze the specimens. These programs were developed by Rolf and Klingenberg to analyze subtle differences in morphology. The first program is TPS-UTIL, which converts our image files in PNG and JPG formats to TPS files. These files can be used in TPS-DIG to position each landmark onto the specimens. Lastly, MorphoJ is a program that actually performs the analyses and gives us tangible data. I came up with two possible hypotheses to answer my previously stated research question. First being that these morphotypes represent the SB and SC elements of the Dapsilotus obliquicostatus. If this is true, then the data points in the analysis would be tightly grouped by morphotype and share less overlap between individuals from each morphotype. The second hypothesis would be that the morphometric analyses cannot distinguish between the morphotypes. And in this case, the data points in the analysis would not show two discrete groups, but rather a mix of overlapping space. This figure shows the locality from which we collected the SBC elements of Dapsilotus obliquicostatus used in this study. The fossils were gathered from the Schleimer No. 1 core, shown here, in the St. Clair Formation in Illinois. When my mentor, Dr. Neil McAdams, was examining these samples as part of her separate study, she noticed that there were two distinct morphotypes present in the core, curved and regular. We believe that the curved samples correlate to the SC elements, while the regular samples correlate to the SB elements. For the rest of this presentation, The curved morphotype and associated data will be presented in red, shown here, while the regular form will be represented in blue. This figure shows the approximate stratigraphic ranges of the recovered samples in feet. As you can see, there is considerable overlap between these morphotypes. Here are the elements themselves. Due to unforeseen circumstances caused by COVID-19, this study was limited to a small sample size of 17 specimens with 9 regular and 8 curved. These are the dextral and sinistral adaxial SBC elements of Dapsilotus obliquicostatus. The sinistral elements were mirrored in Photoshop to achieve the same orientation as the dextral elements. You can see here that the regular morphotype, pictured in the top row, has a sharp curve to its cusp as well as an equilateral basal cavity. The curved type, shown below, has a shallower curve to the cusp as well as a distinct curve in the basal cavity. Geometric morphometric analyses can assess whether regular and curved represent an overlapping range of morphology or whether they are distinct categories. In landmark-based geometric morphometrics, you must first assign landmarks to the form of the specimen so that the software can analyze any shift in morphology. And that's what we did here in Figure A. The landmarks in this study were chosen based off the curvature of the cusp and basal cavity, as well as the curvature and extent of the carina, which is this ridge on the side of the element shown here. In the B diagram, this shows the results of the Procrustes analysis used to examine the variability of landmarks from specimen to specimen. Each point in these data clouds represents surrounding the landmarks mark the position of that individual landmark on each sample, while the blue dot represents the average position of the landmarks. This step is important because it scales the individual elements relative to each other so that the size does not influence the data. This chart gives the placement of each landmark on each morphological feature observed on the SBC samples of Dapsilotus obliquicostatus that best describe the samples. And that's just a verbal way of saying where we placed each of these landmarks. This figure shows the results of the principal component analysis. It's often used to make complex multivariate data easy to explore and visualize. The axes on the scatter plot account for the amount of variation in shape of the samples, and they are correlated to differences in aspects of the shape of the elements. These results are very promising because we did not tell the program to divide the samples based off of their morphotype. The software simply looked for the maximum variability between all individuals and naturally came to that conclusion. So you can see here that each morphotype is mostly within its own group, with only some overlap between here and here. These wireframes show the average Procrustes shape in the lighter color with open dots, and the target shape generated by the principal component analysis in the dark color with closed dots. You can see the sharp curve of the cusp on the left and the shallow curve on the right, so curved and regular forms. And these wireframes would be generated about here for the regular and here for the curved. This figure was generated from the results of the canonical variate analysis, which finds a maximum separation of predefined groups. We told the program what to look for here. We only had 2 variants, so a histogram was generated to illustrate the difference. There can be an infinite number of variants, which would plot on scatterplot. The separation between variant groups tells you how different they are to each other. As you can see, there is no overlap between the groups here, which means that there is a significant degree of difference. These wireframes were generated from the CVA data to illustrate which features most define the classification between the curved and regular morphotypes. Beginning from the far left, this wireframe does not exist and was generated to exaggerate the features of the curved type. The next wireframe shows the average shape of the curved type, which can be seen on the graph. So at negative 4.5, it'd be about right here. The next wireframe shows the average shape of the middle frame. Sorry, the middle frame does not exist. but it represents the average of both morphotypes together. So this would be generated from about this space right here. The next wireframe shows the average shape of the regular morphotype at 4.5, so that would be about right here. And the last wireframe also does not exist, as it's just an exaggeration of the features of the regular type. So you can see the sharp curvature here, and on the exaggeration, you can see the shallow curvature in the cusp. So as for our tentative conclusions that we reached from this study, our preliminary results suggest that the landmark-based geometric morphometrics can in fact be used to determine SB and SC elements. However, as this is a novel study with a limited sample size, further tests are needed to reach a conclusive answer as to whether morphometrics can be applied to coniform codons in general. The promising results of the preliminary analysis open up possibilities for further research. The next step would be to simply increase the sample size of SPC elements to reinforce the initial findings presented by the smaller selection. Specimens could be collected from different localities and age ranges to see if the morphotypes can be discriminated reliably. Other methods of morphology analysis, such as the program shape, may provide additional information for our research. Furthermore, the methods established here could be used to perform similar analyses on other coniform elements and possibly establish better understanding of coniform codon apparatuses, for many of which have similar confusing symmetry transition series. Closing up, I'd just like to acknowledge a few people, beginning with Dr. Neil McAdams, my mentor for the McNair Scholars Program, as well as Dr. James Barrick, Mr. Nicholas Hogenkamp, and Dr. Brad Kramer, who provided invaluable guidance during our research. They're experts in their fields, and they provided a lot of valuable insight. Next up are Dr. John McCryder and Ms. Latricia Phillips, who are the advisors for the McNair Scholars Program here at Texas Tech. They guided me along with my research as well. I'd also like to acknowledge Texas Tech University as a whole, as well as my fellow McNair scholars. Here are the references that we used here in the slideshow. And if you have any questions, feel free to email me here at this address. Thank you for your time.